Cool. All right, I'm gonna just make sure that all of my stuff is working before I get started with math. We'll get started in just a minute. Oh, that looks great. What? What's going on? Cool. All right, good enough for me. I just want to check and make sure it's working. I want to retweet. Okay, so I'm gonna go ahead and get started. I just spent a solid 30 plus minutes working through the first 5 problems of this practice test before I realized that I did not click the start broadcast button. So now I've done that, and I'm gonna work through this stuff and hope it helps somebody. And this is great. Technology is the best. So what I want to do is 2 things. Talk about what to expect on the test, and then work through some of the problems on the practice test if I get some other questions between now and then from the bookwork or worksheets or whatnot, or just in general. I'll be glad to work those out as well. So what to expect on the test? Flipping through the unit plan from this unit, unit 2. We started off with 2A, which was on modeling functions. So given a set of data, be able to enter it in your calculator, view it as a scatter plot, determine a appropriate model if you're not given a specific type of model to use, fit that equation, view the graph of that equation on top of the scatter plot, determine if it's a good fit, and then make predictions from that model. So that was 2A. 2B we did in class on day 1 after we talked about 9A and after we modeled the Cape Fear River data. We talked about power functions. So we kind of just looked at the graphs of each of our basic power functions, and we talked about the patterns of odd versus even powered power functions, and specifically their in behavior and how the in behavior is the same for even powered functions and the same for odd powered functions. And then in 2C, we talked about roots and multiplicity of roots if you're given factored form. So make sure you're comfortable if you're given factored form to determine what the roots of a function are and what their multiplicity is, and if that what that tells you about whether they cross or touch the graph. And also be able to come up with a sketch of that function based on those roots, their multiplicity, and whether it is an even or odd function, and whether it has a positive or negative leading coefficient. In 2C, we also talked about analyzing graphs. So if you're given the graph instead of the equation, come up with the degree, the number of complex roots, which is the same as the degree, whether it has a positive or negative leading coefficient, and then how many positive roots, negative roots, and how many imaginary roots from just the graph. In 2D, we talked about real zeros of polynomial functions. There were a couple of theorems and methods before that. We talked about long division and synthetic division. We looked at the remainder theorem. Let's see. Let's flip back to that real quick. 2D, we talked about, the remainder theorem. We talked about the factor theorem. We talked about coming up with factored form if we're given like a certain number of points or a table of values with the function, making sure they include some zeros in there. And then how to find the roots if we're given a polynomial function in standard form, and write it in factored form from those roots. Oh, also looked at the rational zeros theorem, which just gave us a list of possible rational zeros using our P's and Q's. Okay, let's see, what else? 2E was next. Was just a view of complex numbers, how to identify them, how to work with that imaginary constant, and then how to add, subtract, multiply, and use the conjugate to rationalize the denominator of complex numbers. And then let's see, review of the importance of the discriminant in a quadratic, and then how to plot a complex number on the complex plane, since we can't see those in the real coordinate plane, the Cartesian coordinate plane. And then just a couple of basic operations on the complex plane, be able to find the absolute value, the modulus, which is just the distance from the origin, 0, and then distance between 2 points and midpoint between 2 points on the complex plane. And then lastly, 2F was just combining 2D and 2E together, looking at finding polynomial functions given roots, which could be complex, or which could be imaginary, could be real. And also, given a polynomial in standard form, coming up with its linear factorization. So working through the whole process of finding the roots, both real and imaginary. So for your test, you can expect to see questions from each section. Yeah, you'll have your calculator for the whole thing. And a lot of these practice test questions are good, so I want to work through some of those. So starting with number 1 on the practice test. Apologies, I didn't have a blank copy of the practice test. I'm just working through the answer key, which is linked on the Unit 2 web page. If you haven't found it or if you need it, it's in the extra help or the link section at the bottom of the Unit 2 page, resources section on the website. Excuse me. Goodness. All right, so number 1, find a polynomial of least degree in standard form that has roots -3, -2, and 5, and goes through the point 1, -96. So make sure on your test that you read the directions, and if you're a fan of underlining or highlighting, then I would underline the fact that this is standard form, which is what they want our answer in. We're going to start in factored form and move to standard form after that. I just want to make sure. Yep, I'm live. All right. So let's start with the roots. We know that for each root, there is a factor associated with that root, x minus that root c. So in this problem, each of these are c values. Sometimes they call them c, sometimes they call them r, whatever. They're just roots. They're x-intercepts. Given each one its own factor. So x minus a -3 is x plus 3. X minus a -2 is x plus 2, and so on, x minus 5. So putting those into factored form, and then putting this a coefficient out front, our leading coefficient, to kind of let us know that there may be a vertical stretch or a flip factor to this. And we don't know what that is yet, but we're going to find out in just a moment. So to find out what that a value is before we multiply this stuff out, I'm going to take that extra point that they give us, 1, -96. And that's the x and a y value, because any point on your graph has a x and a y value that should satisfy this equation that we're looking for. So I'm going to plug in that 1 into each of our x's, and I'm going to plug in that -96 into our y, which is just our f of x. You can always replace f of x with the y variable for our purposes. So do that, and then the only unknown is going to be an a. So simplify, do your order of operations, get that a by itself, do your 2-3-step equation solving, and we find out that our a value is 2. So replace that a with 2. And then what I like to do is multiply these factors through first, and then multiply that product by our a value 2. All right, so x plus 3 times x plus 2. Use the box method, use FOIL, use double distributive, whatever works best for you for multiplying two binomials together. But you're going to get this trinomial here. Then take that and multiply it by that third factor, x minus 5. If you're a box method fan, then you're going to do a 2×3 box. If you're FOIL, just make sure you get all 6 of those terms and combine them. Combine those like terms. You're going to get x cubed minus 19x minus 30. Don't forget about that 2, that a coefficient. Distribute that 2 to each of those terms. So our final answer should be 2x cubed minus 38x minus 60. If I were taking a test and I saw a problem like this, I would star this problem and then work out the rest of the test as best I could, and then come back to this problem if I had extra time, and then I would graph that final equation answer into my graphing calculator and test it and see if it does have roots at these 3 points. And if it does go through that point, just to check my work. It's a great way to check your work is to graph it. Again, you're going to have your calculator for the whole test. So I want you to use that to your advantage, but I don't want you to waste time with it or try to use it for things it wasn't intended to be used for. All right, next problem, number 2. Divide the polynomial f of x by d of x. So the first polynomial goes underneath the house. The second polynomial goes outside of the house. And I've gotten this all written on because I just worked out this problem a few minutes ago before you guys joined me. So we say, what can I multiply this leading term by 2x to get this leading term for x cubed? So that's going to be 2x squared. So we take that 2x squared, multiply it by both terms on the outside to get what's underneath here. Don't forget to subtract. Put that in parentheses if you need to. Bring down your next term. And do the same thing. What can I multiply by 2x to get negative 10x squared? Well, I got to have a negative. I got to have, let's see, 2 times 5 is 10. And then I got to have another x factor. So negative 5x, that goes on top. And then we're going to multiply that by 2x plus 1 again, put it underneath. We're going to subtract. Don't forget those parentheses. Unless you're just awesome at remembering to subtract and you never make mistakes. And then bring down our constant if we've got it. And also don't forget if you have any missing degree terms. So like, for example, if we didn't have this 2x term, we would want to put a 0x here as a placeholder. We got to have each degree accounted for when we do our long division, okay? Or else it's gonna mess up the process. So we get all the way down. When we get down here, we've got the same degree term as we have on the outside of our division symbol here. So 2 doesn't go into 7 evenly, but don't let that freak you out. If this happens on the test, hint, hint, wink, wink, nod, nod is going to. Just take whatever you've got down here and divide it by that leading term. So 7x over 2x. Well, the x's are going to cancel out. You're going to be left with 7 over 2. I'm okay if you write it like that. 7 over 2. I'm okay if you write it as 3.5 or as 3.5. I don't care. Any of those three are okay. But that's going to be your last part of your answer before we get to the remainder. Again, it's okay for that to have a fraction or a decimal in it. That's just how it goes sometimes. Write that out. Distribute it to each one. And then subtract 1 last time. You're going to get, in this case, negative 4.5 as your remainder. So remember, with the remainder, we're going to copy down everything on top of our division bar. And then our remainder goes on top of what we were dividing by on the outside. Okay, make sure you write that summary statement just like that. Don't just circle what's on top of your fraction bar. All right, let's speed this up a little bit. Number 3. On the practice test says find all zeros. They give us factored form. They give us a table. They also want us to state the multiplicity and whether that implies that it touches or crosses. That would be weird if it crotches. Touches or crosses at each 0. So we take each one. First one, for example, x plus 1, set it equal to 0 to find that 0. Solve for x. Negative 1 is our first 0. And then we steal that degree. That is our multiplicity. You don't have to do any operations to it as long as what you're given is in factored form. Don't mess with it. Just take that exponent. That's your multiplicity. If it's even, it touches at that point. All right, so it's just going to come down to negative 1 and boop, touch it and stay in whatever quadrant it was in before. Going to our next 0, 2. So if we take x minus 2, set it equal to 0, then we get 2 as our 0. Its multiplicity is 1 because it has that invisible exponent up there. 1 is odd, so it's going to cross at our 0 of 2. The last 0, x minus 3, set it equal to 0, solve, you're going to get 3. That's your last 0. It has an exponent of 3 outside of that factor. So that's our multiplicity. 3 is odd, so it's going to cross at that one as well. All right, so the purposes of this problem, that's done. But if you were asked to sketch a graph of this function, then what you could do is you could say, well, all right, that's cool. You could say, all right, I know I've got a 0 at -1, 2, and 3, so plot those zeros. -1, 2, and 3. And then add up all your multiplicities. So 3 and 1 is 4, plus 2 is 6. 6 is even, so you know it's going to have either this shape or this shape overall, just kind of looking at the end behavior. Leading coefficient is 1. 1 is positive, so we know it's going to be opening up instead of opening down. All right, so I would go ahead and kind of sketch in my end behavior like so. So I know where it's coming from and where it's going overall. All right, and then using our multiplicities, it's going to come down. It's going to make this parabolic shape at -1 because it has a multiplicity of 2. It's a double root. At the 0 of 2, got a multiplicity of 1. So it's just going to cross straight through. If you zoomed in on that on a graph, it would look linear, just right around that section. And then at 3, it's going to look cubic because it has a multiplicity of 3. So notice how I've kind of sketched it where it doesn't just come cross straight through like it did with 2. It kind of comes up and flattens out a bit before it moves on and completes that end behavior of a positive 4th degree polynomial function. Cool. So that would be a sketch. Again, the height of these little local extrema don't matter on our sketch. All right. Number 4. If you're asked if a linear binomial is a factor of a big old polynomial, again, that goes back to section 2D, where you've got 2 options. You could do 3 options. You could do long division. If your remainder is 0, it is a factor. You could do synthetic division. If your remainder is 0, you could, if your remainder is 0, it would also be a factor. But notice it's we're in double digits degrees here. You got to be careful about doing longer synthetic division with double digits degrees, because from 5, 4, 3, 2, 1, all those 0 placeholders. And that's totally fine to do. Just be careful on your mental math and on your arithmetic. A quicker way to do it is to use that, I believe it was called a remainder theorem from 2D. On that second page, yeah, it said that the remainder is the same as the function value f of c. So let's do that. That's the shorter version. So we're just going to do f of c. C in this case is -1. We put that x plus 1 equal to 0 and solve. And then we're just going to sub it in. Remember, -1, a negative number to any even power is going to be positive. To any odd power is going to be negative. Remember, we do those exponents before you do the signs out front. Simplify. You can use your calculator if you'd like. Although be careful, make sure you plug in -1 in parentheses each time. Simplify, and we get 2. 2 is not 0, so x plus 1 is not a factor, nor is -1 a root of this function. You can graph it and check it if you want to make sure. All right, let's speed this up, moving right along. On the next page, number 5, skip it. We didn't talk about Descartes' rule of signs. That's for if I were not letting you use your calculator for a question like this, but I am. So we're going to use our calculator to help us instead of this task, which nobody uses if they have access to a calculator anymore. Number 6 is useful. We have talked about the rational root theorem. So remember, that's our P's and our Q's. P's are factors of the constant. Q's are factors of the leading coefficient. You want to look for any combination of the factors of P divided by the factors, or if you speak English, the factors of Q. So P over Q, list them all out. Those are our possible rational roots. We did not talk about upper bounds, so skip a question like number 7. We did not talk about the P minus MQ method. Again, those are useful if we don't have access to technology and we don't want to do synthetic division, however many times this is. So we're going to skip on down to number 9 where it says find all of the rational zeros for the function. At this point, I would go back to the given function that's in standard form and say, all right, what's my degree? The degree is that biggest exponent. That's going to be 4. So we know that we're going to have 4 complex roots. Remember, complex could be both real or imaginary. So we know we're going to have 4 overall. I will not give you a problem where you have both irrational and imaginary roots. It will be one or the other. And it will also definitely have at least one rational root. It's going to be at least cubic. So in order to find that rational root, or maybe even get an idea of the irrational, although it won't help us with the imaginary, let's graph it. So go into your TI whatnot and plug in the function that they gave you at the beginning of the problem. Be careful to plug it in accurately. Take your time to double check that. And then I like to do zoom 6 to kind of get us in our window. Once it graphs it, make sure that you consider, use common sense. So you know it's going to be a 4th degree. So you kind of know that the M behavior is going to be the same. It's a positive leading coefficient, so we know it's going to open up. So I don't know, maybe there's more down here or up here. Maybe it comes back down. I'm not sure. So I'm going to change my window a little bit. I'm going to change my X max to maybe 20. I don't know. This kind of thing you can kind of guess and check with. And there may be some little local extrema down lower than -10. It's not really important, but just out of curiosity, I'm going to change that one as well. All right, and then I'm going to graph it. Okay, so I'm not going to give you any roots that are outside of the range of like -20 to +20. So I feel pretty good that these are the two. These are the two real roots that we're going to be working with. This one right here looks like it's around 2. If I were to say trace 2. Okay, so that's a 0 right there. So we're definitely going to use 2. This one looks like it's, I don't know, -1.5 or something. Let's try -1.5. Oops. -1.5. Okay, so that's the root 2. You could zoom in on that if you didn't use the trace function. But those look like our 2 rational roots. If we weren't sure what they were, if you didn't want to use trace or the what do we do? Second calc and find the 0 deal, then you could look back at your list of possible rational roots and see what is around that location. See what makes sense for that. So we said 2 and -1.5. So the next thing you want to do, and even though we know that 2 is a 0, you still need to do synthetic division for those points, because doing so is going to allow you to find either the exact irrational or complex roots. All right, I don't want any rounding of decimals on this part of the test. All right, so 2. We're going to try 2 using the division, pull all those coefficients out, drop down the first one, multiply it by that addict number. And then remember, instead of division, you are adding. So add, repeat until you get down to the last column, which if 2 is truly a 0, it should give you a 0 remainder, which it does. So 2 is definitely one of our rational zeros. So the next thing I want to do is I want to take what's left over in that row. So now I've got, let's see, constant, linear, quadratic, cubic here. And I want to test the other root. Okay, so we saw a negative 3.5 for the other one. Ignore this work. This work was done with the 6 and the negative 4 and the positive 3/2. That work was done before I had a calculator. So I'm going to test negative 3.5, negative 3/2 with that row of 4. Boom, we get a 0 remainder. So that is our other rational root. And again, the key here, the important part here, is that it leaves us with a quadratic. Okay, so this leaves us with this being 2x squared minus 12x plus 20. So we're going to set that equal to 0, and you're going to use quadratic formula and solve that puppy. Whatever you get is going to tell you your remaining roots. Okay, in this example here, I wrote out the 2 factors that we already knew from the 2 zeros that we found. And then I factored out a 2. It's not really important, but I factored out a 2 since that was a common factor in that trinomial. And then did quadratic formula. That'll just make your numbers a little bit smaller, a little more manageable. But if you did quadratic formula with this guy here, and used your A as 2, your B as negative 12, and your C as 20, you should get the same solution. So make sure you're comfortable with quadratic formula. Simplify that discriminant. We got a negative discriminant, so we're going to get imaginary answers. Simplify. It's okay to leave your roots as plus minus, but then when you go to put it in as factors, make sure you separate them into 2 factors. All right, so we can see we've got 2 imaginary roots, which makes sense because if we go back to our graph, we only saw 2 real roots. So we shouldn't be looking for other irrational ones. We should be looking for the imaginary ones that don't show up on our Cartesian coordinate plane. Whew, how we doing? All right. Let's work through these last couple problems, and then I think we'll wrap it up. All right, section 3 says finding roots graphically. We're asked to list the number of complex roots, the sign of the leading coefficient, and the number of positive, negative, and imaginary roots. If we're only given the graph, we're not given any equations in this part. Okay. So this first guy here. First thing I see is that it has different end behavior on the 2 ends. So I know it's going to be an odd degree. So then we're going to go in and we're going to draw these vertical lines everywhere we see extrema. Okay, so this little minimum, this local maximum, this minimum, this maximum. And then anywhere you see this little flattening out, this saddle point, that shows it's got a cubic behavior right here. Okay, it doesn't just go straight through that 0. It kind of flattens out like a cubic does. Then you want to draw 2 of those vertical lines. Once we do that, pretend those lines are like separating different sections of your graph. We want to count those sections, not the lines, but the sections. You can just add 1 to the number of lines if you want to do that. But 1, 2, 3, 4, 5, 6, 7. 7 sections. That makes sense. It's odd. So we have different end behaviors. So 7 is our degree. It's also the number of complex roots. Next thing it asks for the sign of the leading coefficient. So remember, if it was positive, then our graph would have end behavior like so. But it is negative because it has an overall decreasing end behavior. So it starts going down, and then after it gets through all these tweaks, then it is decreasing. Okay, part C, what do they ask for? The number of positive roots. So we can just look at that and say, well, this is a positive root here. There's 1. And this guy here, remember, this was a triple. So we really just have 2 positive roots. But one of them counts for 1. It's a single, but the other one counts for 3 of our 7 total roots because it's a triple root. It has a multiplicity of 3. All right, part D asks us for negative roots. So we have a negative root here, but again, it comes down and just touches before it goes on up. So that's going to be a double root. So one root, but it counts for 2. So then to find the number of imaginary roots, then we have 7. We have one single root. We have a triple root, which counts for 3. We have a double negative root, which counts for 2. Add those up. We get 1, 2, 3, 4, 5, 6. Does that make any sense? Oh, don't forget your 0. I don't ask for you to list how many roots go through the origin, but don't forget to count that. That's a root. Plus 1. So that's 7 of the roots accounted for. Subtract that from our degree, and that tells you how many imaginary roots we have. Cool. Same thing with this guy. We've got 2 negative roots, 2 positive roots. They all look like single roots. We've got that same end behavior on each side, so we know it's going to be an even degree or even number of complex roots. Put your divisions in at each extrema. We have 4 sections, so our degree, our complex roots are 4. It opens up, so it's going to be positive leading coefficient. Again, 2 positive, 2 negative. Add those up, we get 4. Again, no imaginary roots for this one. Remember, we can't see imaginary roots on the graph, so we got to rely on accounting for all of our roots in our graph. All right, this last one, cubic. We've got a local max here, local minimum here. So we have 3 sections. It is increasing overall, so it's going to be a positive leading coefficient. Again, you can kind of compare this to like the parent function or the power function, x cubed. Think about the end behavior of that. Matches with that guy. We've got 1 positive root, but it's a double because it just comes down and touches, kind of like a parabola. If you were to just zoom in on this section, it would look like a parabola, a quadratic, which has a power of 2. So that's going to count for 2. We've got 1 negative root that just straight crosses, so that's going to count for 1. Add those up, subtract your number of complex roots. That's going to tell you how many imaginary roots you have, 0. Skip question 15. We did not talk about this because we have technology. Although this is a really cool way to approximate roots without a graphing calculator. If you're interested, it won't be on the test though. And then the bonus. This is similar to a question earlier where you're given a bunch of roots and asked to come up with an equation. It doesn't tell us to write it in standard form, so factored form is just fine. But remember that factor theorem that if a number is a root, then x minus that number is a factor. So pair each root with a factor. They tell us we have a double root at x minus 2, so make sure you give that x plus 2 a multiplicity of 2. Same thing we did with the, I think it was it number 2 or number 3 on the front page? Number, where was it? Oh, it was number 1. Number 1, where we were given that extra point, and after we found all our factors, we plugged that point into x and y and solved for a. So same deal with this one. Look out. Plug in that 0, 80, that y-intercept to find your a value, which is going to be a -1. And make sure you include that -1. Cool. Hope this helped. Peace.